Okay, hello everyone. So today we're going to be talking about ordinary least squares or regression. Um, the regression model here that we're going to talk about is really the workhorse for modern statistics and econometrics. So we'll be spending all of the lecture video today will be related to how we estimate OLS regression, both in theory and in practice using R. So I'm going to try to split this lecture up into several different videos that really go from just a very general review to a graphical example to some implementation in R and then to some examples, concrete examples. So for the first video here, it'll be short, just a very general introduction, hopefully a review for most of you who have taken other econometric or stat courses. We're going to have some kind of a model or a function here where our y is going to be an outcome variable of our interests as a function of some x's, which are our observed variables. We have some betas here, which are our parameters that we'll be estimating. And then we have this epsilon term, which is our residual term or our unobservable. So we have and we'll go over this in some of the assumptions of OLS, but we assume that this function is going to be of a linear form, where the relationship between x and y is linear, and that we assume that the epsilon or the error term enters into the equation additively. So there's a lot of focus in econ and in stats in interpreting what this epsilon or what this error term is. There's a lot of different ways that we can interpret it. But it is very important for estimating our model, and in particular, as we'll see later on, we'll be doing our model diagnostics, in large part looking at how this error term looks graphically as a way of telling us whether or not our model is behaving properly or not. So this epsilon term is extremely important to understand, so we'll practice with understanding what the error term is and what it's trying to capture. In general, we know some observable variables we have in X. So if we knew beta, we would know everything that we need to predict what Y is going to be, our outcome variable of interest. So the error term is essentially measuring what our ignorance is in terms of what we can't see or what we can't observe. And this is probably the main interpretation that it has is capturing all of the information that we don't actually observe in the real world besides our observed variables x. Okay, so it's all our unmodeled factors and left out variables. It's also considered to have importance interpreting measurement error in our outcome variable of interest. It could also be interpreted as, the epsilon could be interpreted as the unobserved heterogeneity, or the sum of random stuff, which is independent of x, or some random shifters like business cycles or the weather. Okay, so for equation 2, that we see here, our linear model y is a function of x beta plus the epsilon term. We can redefine our equation in terms of epsilon, where epsilon is going to be obtained, or error term is going to be obtained by subtracting x beta from our observed variable y. So we can write our error term in this format, which will be important for our next steps later on. But for now, what we want to assume is that this error term, the bigger it is, it means that there's more error in our model. That means we're not predicting y very good based on our observed x's and the parameters of our interest. So the way that we set up our model is we want to minimize the error in our model. So we assume the prediction error is bad. We're going to minimize the weighted sum of the error, or of the residuals, through this equation here, where again, we're summing up all of our individual error terms for each of our data points, and we're going to weight it by some omega I. and we're going to sum all these errors up, and we're going to minimize have the minimum of the error to obtain our estimate for our beta, which is our parameter that defines our relationship between x and y. So when we assign the weight for our omega here as being the size of epsilon itself, that is, we're going to substitute our omega for our weight as being the actual size of the error itself, we're going to get the OLS parameter for obtaining beta. And so this is going to become the sum, minimizing the sum of the squared residuals here. Epsilon times epsilon is going to be the squared epsilon. And if we subtract or substitute our equation for how we define epsilon, which we obtain here, y minus xb, we can substitute the epsilon for y minus xb and y minus xb, and we can have, again, the same equation written out differently, where we're going to be basically minimizing the difference y minus xb squared, and we're going to be summating the y minus xb squared in order to get our parameter for beta. Okay, so in this video, we just look at a very brief introduction. The next video here, we're going to give a graphical example to try to explain exactly what we're minimizing here in terms of the minimizing the sum of squared errors. So stay tuned for that video.